In section 531, we're going to take a look at the fundamental theorem of algebra. We're going to define the fundamental theorem of algebra, understand the number of real roots and imaginary roots a polynomial function can have, and determine the number of real roots a polynomial can have. And the caveat, they're going to be possibilities. So if we look at these two examples here, I can look at this and be like, oh, there's two roots. If I were to consider the lowest possible polynomial, that's going to be x squared. There's three roots. The lowest possible polynomial, that's going to be something x cubed, right? Because I have three zeros. X minus my 0, x minus my 0, x minus my 0. That's three of them, x cubed. Now, what happens if I shift the graph up? Well, it's not crossing the x-axis anymore, but it's still x squared. It's only crossing once now, but it's still x cubed. What ended up happening was our real roots were kind of exchanged for these imaginary roots. Now, the cool thing about it is that number, the degree, did not change. So that leads to the fundamental theorem of algebra. And that basically says that if a polynomial function of degree n, the graph of the function has at most n real zeros, and which means x-intercepts. It's implying that the highest exponent is how many roots, including multiplicity, the polynomial has. Now, we can take this a step further and say also complex roots. Right? That n degree means how many complex roots, if you include a multiplicity, that polynomial is going to have. That's the fundamental theorem of algebra. You can look at the degree and you can make some small assumption about how the roots are going to be, how many roots that I have in that polynomial. So in this example, I have x cubed. Because my degree is 3, which is the highest exponent, I know it has a maximum of 3 roots. It could be, negative 3, multiplicity 3, right? But that's what I mean by counting multiplicity, is if you have repeats, you count that towards the number for n. So how many possible roots here? We said it was 3, right? We have that one there, and then we have the other 2. Now, we can create a map of what this possibility can be with what we call Descartes' rule of signs. Now, it seems a little complicated. It's much easier than it appears. Like, you look at this and you're like, wow, this is a lot of words. But the process is actually kind of simple. It says you need to look at the function in two manners. P of positive x and P of negative x. P of positive x is the number of positive real zeros. And then the P of negative x is going to be the number of negative zeros. Now, what you do in both scenarios is you just count the number of times the sign changes. So you just go through and you count it. It changes from positive negative or negative positive. So you count by that number. And then what you have to do is you just kind of count down, because remember we said we might have complex zeros. If going back to this example right here, right? I had x cubed, I had 3 roots, but what ended up happening? Those 3 roots, 2 of them turned into imaginary. 2 of them turned into imaginary. So that can happen as well. Is that basically 2 are converting into imaginary. So once you find that number, you just count down by an even integer. So by 2, by 2, by 2, by 2. And what you're essentially doing is you're exchanging them for those imaginary possibilities. And we're able to create a map of this. So I know it's weird, like I said, but let's piece that together. So let's look at, in this case, positive f of x. Let's count the number of times the sign changes. So I didn't have to change anything. So it changes from positive to negative, and then that's the same. It's negative to negative. and then it goes from negative to positive. So that's 2 changes. So I'm going to say it has 2 positive zeros, but then we do that weird exchange where they might be complex numbers. So I count down by 2. 2 minus 2 gives me 0. So I have 2 possible scenarios. I could have 2 positive zeros or 0 positive zeros. Now we do the same thing for f of negative x. This is for the negative zeros, right? Positive x, positive zeros, negative x, negative zeros. Now you just need to simplify it. Negative x to the 5th power, negative, 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 right? So that changes the sign. So you go through and you reduce that. Negative x squared, okay, it stays the same. Negative, negative is a positive, etc., etc. Now you do the same thing. You just count it. Negative to negative, no change. Negative to positive, 1 change. Positive to positive, no change. So I only have 1 possible negative 0. Now, what I can actually do is I can piece this together and I can actually map out what my different scenarios are going to be. So in this chart here, I basically put every combination with this number and pair it with every combination of that number. So I have 2 positive zeros and 1 negative 0. I have 0 positive zeros and 1 negative 0. Seems to be the only possibilities, right? 2 and 1 and 0 and 1. So then I can fill in the imaginary zeros because my n is 5, right? Our degree is 5. So I could have these 2 possible scenarios here. So it could either be this scenario 1, which is I have 2 positive zeros, 1 negative 0, and 2 imaginary. Or it could be this second scenario where it's 1 negative 0 and 4 imaginary zeros. Let's look at another one. Remember, 2 scenarios, f of positive x and f of negative x. F of positive x is positive zeros, f of negative x, negative zeros. So I count the number of signs. Positive to negative, negative to positive, positive to negative, negative to positive. Okay, so that's 4. Now I need to count down by 2. So 4 minus 2 is 2, 2 minus 2 is 0. So I have these 3 different possibilities. Now, let's find the negative zeros, or the possibilities for that. So I plug in negative x. Simplify it. Negative x to the 4th, right? It's 4 negatives, stays the same. Odd numbers changes. Even numbers stays the same. Odd numbers changes. It's kind of an easy way to do it. Now I go through and count it. They all stay the same, right? There's no sign changes. So I have 0 negative zeros. So now I combine them all together. I have 4 and 0, 2 and 0, and 0 and 0. So now this means that I have 0 imaginary zeros. It crosses it 4 times, crosses it twice, and then doesn't cross at all the x-axis, and I just have 4 imaginary zeros. Now the cool thing about this, and what it means by positive zeros and negative zeros, is literally where it is on the x-axis. So in this scenario here, this is saying that this graph, 1, 2, 3, 4, crosses 4 times in the positive. This one is saying it crosses only 2 times in the positive. Something like that. And then this one is saying it doesn't even cross at all. Right? It could be one of these 3 scenarios. Enter this into Desmos and take a look. It'll verify it's going to be one of these 3 scenarios, which is kind of cool. All right, I'll give you a moment to practice this one. So what did we learn today? We talked about the fundamental theorem of algebra and Descartes' rule of signs. So what was the fundamental theorem of algebra? It basically says whatever the degree is of your polynomial, so your n, the degree, that tells you the number of complex roots. So if your n is 8, including multiplicity, right, that means you can have up to 8 zeros, both imaginary and real. And if you have multiplicity, you just count it twice or 3 times or 4 times, depending on what your multiplicity is. Now, do complex roots come in conjugate pairs? Yes, which is the reason why, for Descartes' rule of signs, you subtract 2 every time. This does conclude our lesson. If you have any other questions, please leave them in the comments.